PhD seminar of the semester or the academic year. So we're happy to have Professor Shun-Pei Miao from NCKU to give this ending seminar. Professor Miao actually did a master work here under Professor Pei Ho, and then went to the US and received her PhD at Florida University. Actually, her advisor is sitting over there. And then she went on to Utrecht University in the Netherlands. I spent 2 years there, and I went to Chile to the, Centro de Estudios Científicos. Of Chile. She could have stayed on, but she received a 3-year Veni Fellowship and returned to Utrecht. And in 2013, at that end of that fellowship, she became an assistant professor at NCKU, the current position. So today's topic is about quantum gravity, something like that. Okay, so electrodynamics, electrodynamic effects of inflationary gravitons. Okay, listen now.
I would like to thank Professor Shu. It's my pleasure to speak at this theoretical seminar. In this talk, first I will going to give a very quick review of the cosmological background and give a definition of inflation, and we'll also talk about why we have big quantum loop effects during the primordial inflation. And later, I will switch to the main part. The main part, I will talk about the motivation, what is the current project, and I will also report this photon effects gets influenced by virtual gravitons, start from the flat space-time, then effects on de Sitter. And finally, I will going to report the latest result and talk about why we will redo the calculation using a different gauge. Okay. So on a very large scale, what I mean is larger than gauge scale, about 100 megaparsec. And our universe looks very homogeneous and asymptotic. So that means you look at a different direction, you look the same, and you see the different location also look the same. So we use this so-called Frenderer-Robbins-Walker geometry to describe it. And you can see this spatial part of a time-dependent function called scale factor. Okay, and you can imagine the physical distance is not just the coordinate separation, because you can imagine so far our universe is keep expanding, so this time-dependent function is keep increasing. You can see if you just choose arbitrary 2 points on the balloon, and you try to ball the balloon, you can see even the coordinate separation is fixed the same, but you can see the physical distance will change with time, right? So this one, the physical distance is A times this coordinate separation, and you also can see the physical wavelength or momentum get right shift, okay? Because when A is increasing, physical momentum is get right shift. And also, from this geometry, you might say, okay, if we know the scale factor, then we might know everything. However, what we really measured is not the scale factor. What we really measured is some parameter formed by the scale factor. For example, the redshift Hubble parameter, dispersion parameter, or force throw parameter. The redshift, by definition, that is wavelength difference between the current and the wavelength in the past to the photon emitted originally in the past. The wavelength is proportional to the scale factor, so you can get a relation between the redshift and the scale factor. Okay, so this is one, and then you can see A0 is the current Hubble parameter. If you set up this also equal to A0, you will know the current redshift is 0. When you look back into the universe illusion, the redshift become higher and higher. And then the other is we call the Hubble parameter. You can see the first derivative. So this is the concept of velocity. So this tells us whether or not the universe is expanding. Okay. And the distortion parameter, you see the second derivative. So this concept of distortion. So this tells us whether or not our universe is accelerating. But the funny thing is there's minus sign here. So that means if you see the negative value, that is universe is accelerating. Okay. The other related parameter is called the Foster-Storer parameter. It has relation with this distortion parameter. So you can see when this is negative, that means universe is accelerating. So if the Q, the minus 1 plus epsilon less than 0, then epsilon less than 1, universe is accelerating. So you can see from this parameter that tell you the current phase or any, you can pick up any epoch and look at this data, you will know this universe is accelerating expanding or is decelerating expanding. And here is the inflation. What is inflation means? That is you have a positive value of Hubble parameter and a negative value of distortion parameter. So this is accelerating expanding space-time. And our current phase is doing the accelerating expanding. You can see from the Hubble parameter, the current Hubble parameter is positive, even though it's very small. And you also can see the distortion parameter is negative value. Okay. And near the other epoch in our universe, we call the primordial inflation. It's right at the very beginning. You also can see this value gets from the measure the scalar primordial pulse spectrum, and also upper bound of tensor to scalar ratio. You actually can infer how large your GH square. You also can get this Hubble parameter during the primordial inflation. It's very, very big. It's about, if you terms of GeV, it's 10 to 14 GeV. It's 10 to 38 hertz. Okay. You also can see this distortion parameter is negative and more negative than the current phase. So that means during the primordial inflation, it's actually doing more accelerated expanding than the current phase. Okay, because you can see this. And then the other big difference is you can see this Hubble parameter. Okay, the Hubble parameter during the primordial inflation is about 10 to 56 order magnitude bigger than the current one. So the difference between primordial inflation and the current phase, the first is energy scale is much higher. Okay. The second, you see this distortion parameter is more negative, so it's doing actually so far it's maximally accelerated expanding space-time. And you also can infer this Foster-Storer parameter almost to 0. And we know epsilon equal to 0 is de Sitter. So depends on the subject you compute. You see if this is 0, that means H must be constant. That is de Sitter. So that means depending on the quantity you try to compute, most of the case you can approximate primordial inflation as de Sitter space. And this is what I'm doing. Basically, I try to compute I try to search for the quantum effects or quantum loop effects during the primordial inflation. Okay. The question you will ask, okay, can we use the perturbation theory? Of course, we can use the perturbation theory because you can see the loop counting parameter is very small, right? It's about 10 to the minus 11. Even though this is in such a high energy scale, but counting parameter is still very small. So perturbation theory still works. And also you say, okay, this counting parameter is so small, then why bother study anything during the primordial inflation? That is because the background is not space-time. And you see from the Friedman-Robinson worker, in the de Sitter, A is exponential HT, okay? So this background information, when you do some computation in this background, the time-dependent this kind of background information might enter into the quantity you compute. So even though the counting parameter is very small, but the physical observable or anything you try to compute during this in this background might be time dependent. So this time dependent function might finally overcome the smallness of loop counting parameter. So I would say it's not entirely negligible. Even though the counting parameter is very small.
Excuse me. Epsilon is actually a measured number or a theory number?
Actually is not directly measured. is inferred from the major scalar power spectrum. We know the major scalar power spectrum. And it takes the form like GH squared, some number GH squared divided by epsilon. So you can. This is we call the primordial scalar power spectrum, and this is already measured the tree order, and we also know the upper bounds for the tensor to scalar ratio. Okay, using these two effects, then you can infer how large your epsilon. Okay. So this is inferred from the current data. And also, GH squared is loop coming from during the primordial inflation, also inferred from the current data. Even though this is not entirely exact, but this is the most rigorous bound that we can find today. Yeah. So the next question to ask is, okay, we try to search the quantum effects or quantum loop effects during the primordial inflation. Then the question to ask is, okay, what is quantum loop effects? How do we think of it? Usually, you can think of these quantum loop effects as how classical particles interact with virtual particles. So you know how can you get the bigger effects when you have a more chance classical particle and more chance interact with virtual particles, then it brings the bigger effects. Okay. So in the flat space time, you know, the massive particle or very light mass particle live longer than massive one. So this is why we see the electromagnetic force is stronger at a short distance. So this is the same, it's true, during the primordial inflation. So the massive particle or very light mass particle will live longer. The difference during the primordial inflation compared with the flat space time, that is, primordial inflation is maximal the accelerated expanded geometry. So what makes difference? You know the pair of virtual particle emerge from the vacuum and quickly come back to a vacuum. This is the case in the flat space time. Okay, but during the primordial inflation, the pair of virtual particle emerge from the vacuum, and because this space time expanding so much, so quickly, so it's like this virtual particle is to be trapped in the Hubble flow. And in some very low energy case, it even can live forever. So you can see why the quantum loop effects can be bigger during the primordial inflation. That is because the massive particle, okay, they have a chance to live much longer than the flat space time one. So the classical particle can have more chance to interact with the virtual particles, then hence give the bigger effects. And the other thing is, if you have more a virtual particle emerge from the vacuum, okay, classical particle also can interact more with the virtual particles. The funny thing is most massive particles have one property. The property is conformal invariant symmetry. And if the theory has a conformal invariant symmetry, you will suppress the emergence rate from the vacuum. So that is contradictory because we said the massive particle can live longer during the primordial inflation, but not many massive particles emerge from the vacuum. Okay. However, there are two very special kinds of particles. They are massive, but they do not have classical conformal invariance. One is massive minima couple scalar, the other is gravitons. Okay. So actually, you can expect the big effects delivered by these two virtual particles. And actually, we also can look at it quantitatively, how this non-conformal invariant massive particle product. Basically, this dynamical graviton behave like a massive minimum couple scalar. So this is Lagrangian density in the comoving coordinates, and you can find the Lagrangian and do the spatial Fourier transform. Then you find out this Lagrangian looks like a time-dependent simple harmonic oscillator with mass roughly A2 cube, and this angular frequency equal to KC divided by A. You can see one half n x dot square, 1/2 n omega square x square. Okay, so this is a time-dependent simple harmonic oscillator. At this stage, you can easily solve for the mode function because you can easily write down this simple harmonic oscillator. You write down this equation of motion, then you can write down the Heisenberg operator in terms of this mode function multiplied by this creation and annihilation operator. Then you can solve the mode function. Okay. You also can compute the energy. So in the phase-space time, you only get this part that is 1/2 h bar omega. This is 0-point energy. However, during the inflation, you have an extra piece, this n, we call the occupation number. When occupation number becomes significant, when x roughly equal to 1, and this can become very big when x much less than 1. What is x? You can see this is a physical momentum in terms of Hubble parameter. See? Here we have talked about this physical momentum here. So you can see when the particles start to conduct around the Hubble parameter, okay, you will get a lot of particle production. For this method is non-conformal invariant particles. You get a much bigger production when this physical momentum much less than Hubble parameter.
Can you explain that first line? Dynamical gravitons are minimally coupled scalar.
Oh, I mean, its mode function behave the same as the message minima coupled scalar.
What does minimal coupled here mean?
Oh, it's just this term. Minimal coupled means you didn't couple to the metric. If you have R-phi square term, then it's non-minimal coupled. So what I mean is you have this kind of yeah. And before we switch to the main part, I will go to talk about why we want to look at this photon propagated through to the sea of infrared gravitons. Okay, because we want to study how photons behavior changed by this virtual graviton during the primordial inflation. And you say, okay, is this real or something? Actually, it's motivated by my thesis calculation. My thesis calculation is study meshes fermion propagated through the sea of infrared gravitons during the primordial inflation. And we do this in dimensional regression, one loop order. We find out the fermion mode function growing like a logarithm a and one loop order. And okay, and the other model very similar to this. That is meshes minima coupled scalar propagated through to the infrared virtual gravitons during the primordial inflation. But in the meshes particle kind, this meshes particle didn't get influence. It didn't show this infrared logarithm enhancement. Finally, we actually analyze diagram by diagram and find out the enhancement effects, I mean the logarithm A term, actually come from the spin-spin interaction. That is the spin of the fermion coupled to the spin of gravitons. So this is why it gives a very big effects in the fermion mode function. Okay, and for the meshes minima coupled scalar, because meshes minima coupled scalar only have a kinetic term here. You see this meshes minima coupled scalar. So it only can couple to gravitons through this kinetic term, but at the late time, kinetic energy will shift. So this will not have enhancement. The difference, compare this with the fermion. The fermion have spin connection, so it's extra hard. So this is why we get big effects. And the current project is motivated by this because you know photon also have a spin. Okay, so we also expect we can derive the big effects from this model. What we did is try to compute the vacuum polarization at one loop using the dimensional regression. You can see this wavy line stands for the photon. The curly line is gravitons. Okay, And we also renormalize it using the BPHZ counter terms. We have two invariant one and one non-invariant one. Later I will comment why we have this extra term. Okay, so after you get the vacuum polarization, how do you know the fermion behavior changed? The way you do is try to quantum correct Maxwell equation. That means this is a classical term, and this is the extra piece from the effective action. So you solve this perturbatively. In the zeroth order, this zero, you get the zeroth order gauge potential. Then you try to get the next order. You just integrate zeroth order against this vacuum polarization. Then you get the first order. Of course, when you quantum correct the Maxwell equation, you can study dynamical graviton 1. That is, this part is 0. Or you can, for example, put a source for point charge or magnetic dipole moment. So you also can study a different source and see what the photon behave. Then you will say, okay, you say this is vacuum polarization due to the gravitons. But your introduction to the quantum field theory in the space-time, this is a different version of vacuum polarization, because the vacuum polarization is supposed to interact with electron positron, and this is why you call, and later you will polarize vacuum a little bit. This is why we call the vacuum polarization. Here, photons, neither photon nor gravitons are charged, so it's different kind. And why there exist big effects there? How can they deliver the effects? So the thing is, you can think of this pure photon 1. Okay, suppose the dynamical photons have a momentum like this, and the EM force which is carried by virtual photons, and there is a momentum change with time. Okay, and when you have this virtual gravitons exist, okay, then virtual graviton will interact with this guide. It might add or subtract the momentum to this part, and then this will get change of momentum. Okay, you get change of momentum, then you change the force carried by the virtual photons. Okay, so this is why change. And also we have previously mentioned this infrared gravitons keep producing. We actually derive this occupation number when the physical momentum about Hubble parameter you keep producing. Even later, the infrared graviton reshift, but will keep producing because it is non-conformal, method is non-conformal invariant theory, so you keep producing. You can set this physical momentum of virtual gravitons about Hubble scale. Okay, and this physical momentum of gravitons is much larger than the physical momentum of these photons. So you can imagine when they interact with each other, when this virtual gravitons, hits with these photons, okay? And photons have a very small momentum, so you can expect a big change of this virtual photons, and hence you can see the change, okay, carried by virtual photon, and the EM force will be changed. So this is the picture. Here I will start to report the phase space-time result, and the kappa square is just the counting parameter, and this is invariant length without this part invariant length function, and this vacuum polarization takes this form, okay, and we only in the phase space-time we only need this counter terms. After you use this counter term, subtract the ultraviolet divergence, you get the renormalizable one. It takes this form. And you can see just from dimension analysis, you can see you can take extra fold derivative outside. You see this kappa square is mass, dimension mass minus 2, and 1 over delta x 2d minus 2 with d equal to 4 is about dimension mass 6. So dimension mass 6 minus 2 is 4, so you will see this extra fold derivative outside. Okay, so this is renormalized for 1. It's a vacuum polarization. Okay. And when we use this vacuum polarization in phase space-time, try to quantum correct the Maxwell equation here, this one. And find when we set the source equal to 0, there is a dynamical photons behavior. We find no change for dynamical photons. For the point source, we find this is a classical piece, and actually have a correction for the classical piece, this piece. Okay. Actually, this agree with the 1970 Ray Kautsky's calculation. He used a different method to compute, and they are agreed with each other. So actually, you can imagine this extra piece is the zeroth order field. Okay, distort this virtual gravitons, and this virtual gravitons add momentum or subtract momentum to the momentum which carried by the virtual photon. So you have an extra piece in the Coulomb potential. This is the phase space-time result. And this is the de Sitter result. In the de Sitter result, we use the simple representation. Only need this. This is actually the phase space-time piece. And actually, in addition to this phase space-time piece, we have extra piece. Eta here means it's just subtract the temporal part. Okay. And because this extra piece is not covariant, so it's this breadth de Sitter invariance. This is why we need a non-invariant Count term we talked about at the beginning here. It's a non-invariant Count term. And you will ask, okay, why you use this this kind of representation? Why do you not use the de Sitter invariant representation? Is it better because you do not need non-invariant Count term, right? But the thing is, when you try to make a de Sitter invariant representation, that is, you try to make this ordinary derivative to a covariant derivative, okay? And also try to make this part as the de Sitter invariant tensor. It gets vastly complicated, very, very complicated, and very hard to use, okay? And also, it doesn't get rid of de Sitter breaking piece in this structural function, okay? Even you have a de Sitter representation, okay, F and G we call structural function. Even you have a de Sitter, very complicated de Sitter invariant representation in front of it, but when these things act on the structural functions still have de Sitter breaking piece. And actually, Wood, Lehner, and Kokopes, they find a way to convert the representation between this simple representation and the de Sitter invariant representation. So you will ask, okay, why we use the complicated one to do the calculation? Because you already know how to convert to the de Sitter invariant one. And the de Sitter invariant one also do not get rid of de Sitter breaking piece. So why bother use the complicated one? Because this is some criticism by the mathematical oriented physicists. They say, okay, you should just use the de Sitter invariant one. Okay, it's not very similar to use because when they say that means they never really do the calculation. Okay. And also, if you substitute this part, this de Sitter part, into the original one, you can see here. Substitute this vacuum polarization on de Sitter, and you take one extra derivative out, and also you take a partial, take a partial integration, make this derivative acting on the gauge potential, then you can form this form, and it's very simple to use. And also, we solve this probability using the Shun-Pei formulas and just guarantee to get the result real and causal. So this is de Sitter invariant one. After we have that, you can study the dynamical graviton. There is a source equal to 0, and we find out the zeroth order. This mode function, electric part, magnetic part, is exactly the same as the phase space-time. But and this is not surprised because you know the photon in the EM actually is conformal invariant theory, so it must